If you look at the internet, there are lots of definitions of intelligence and AI. So this is one definition of artificial intelligence, which is really the ability of computers or robots to perform tasks that are usually associated with intelligent beings. Right. So nothing very profound, but it's very obvious, right? So first we have to understand what is intelligence, and then we can see what is artificial intelligence. So if I ask you this question, what do you see? And all of us will be able to say, oh, I see the letter A in different weird formats, right? Now, if I ask you this question, have you ever seen this letter A, any of these A's before? And we have never seen an A like this before. And now the question is, if we were a database system, if our brain works like a database system, we would have to have seen all these A's before in order for us to retrieve that these are all A's. But we don't do that. We don't remember that much of data. So we don't store data. What we do, we generalize from all the past learnings and we build models. So we have built a model of what is an A, what is a car, what is a cat, what is a dog, what is a cricket game. So we have built models for everything, and from data we have what we call generalized. What we have done is we have generalized these models, and this is one of the most important qualities of an intelligent system, that it can generalize from few examples, right? So this idea of generalization is very important, and nature has created our brain in such a way that we are able to generalize from examples very quickly. And this is one ability that we are going to use throughout this course. And machine learning is basically the art of generalization, right? With very few examples of something can be generalized, and that is what is one idea of intelligence. Another idea of intelligence is what we call understanding. So let me show you another picture. And if I ask you, what do you see now? So you can pause your video and you can actually try to understand this image. And what is your brain doing during this time is what we call understanding. So what it is doing is that it is trying to assign a meaning to every pixel in the image in such a way that the meaning it assigns to a pixel and the meaning that emerges for the whole image makes sense together. So this is another idea of understanding, that our brain is trying to interpret the whole in the context of the part and the parts in the context of the whole. And it is trying to make sure that everything fits together. So let me give you one example. If you are walking into a mall and you suddenly see a car inside or a bullock cart inside, you're going to say, what is this doing here? Why? Because your brain doesn't correlate these two things together, right? It doesn't say this kind of belongs here. So another example I'll give you in the text world is, let's say I say as soon as, and I ask you what is the next word you should be thinking about. Suddenly the right word will come to you. As soon as possible is the next word, for example, right? So similarly, our brain, when it understands a word in terms of letters, it is trying to say, is the spelling correct? All the letters are in the right order. Then it understands a word. Similarly, when it understands a sentence, it is looking at the words in the right order and trying to interpret the whole, again given the parts, right, in terms of words. So this understanding is now something that we understand what it means, right? So this is another idea of intelligence. There are many subfields and many terminologies that have evolved. So what I'm going to do is, in the next slide, I'll kind of give a sense of these different terminologies and what they mean. And there are subtle differences between these terminologies, right? So a very uber terminology is what we call AI. AI is really the, like we said, the ability of machines uh, to mimic human intelligence. So it's a very, very broad field and a very broad definition of what is artificial intelligence. Now, within that, there is a field called machine learning, which is an ability for a system to learn from examples, right? And this is one part of AI. Learning and interpretation of data we talked about is one part of AI. And machine learning is one part of AI. There are other parts of AI. Um, Now, what is machine learning is, so, instead of teaching you this, how to do an A versus B, if I give you the examples, right? If we give lots of examples of this is one class, this is one class, then can the machine figure it out by itself? What is A versus B? What is dog versus cat, right? What is this emotion versus that emotion, right? So if machines can figure out through examples, not by coding up a set of rules, if machines can figure out through examples what something is, that is machine learning, as opposed to expert based systems, right? So in the olden days, people had created very rule based expert systems that said if this then that, if this then that, and they coded up a lot of rules that were driving a lot of old systems, right? And now we are saying the rule based systems are hard to manage. You may have missed a whole bunch of rules. It's hard to keep up with the rule based system versions and all that. What about if situations change? The rules have to be added. So, rule based expert systems became very complex and cumbersome. And then the birth of machine learning gave us this ability to say, I don't want your rules. I just need labeled data and I will learn the rules myself. And that was the birth of machine learning. So, how do we recognize patterns of cause and effect automatically using statistics and all is machine learning. Now, within machine learning, there is another area called deep learning. So sometimes when the data is not easy, like, we are dealing with genomics data or text data or speech data or image data or video data, the gap between the data and what you're trying to interpret is very large. So for example, when you're watching a video and you're trying to understand whether, there is a goal that happened in a football video or a sixer in a cricket video, the gap between what you see, what your eyes see, the pixels and the frames, and what you're trying to interpret, there's a huge semantic gap between these two, the input and the output. And therefore, simple machine learning algorithms are not enough. So we need many, many layers of interpretation of that data. So the first interpretation may be just, pixels and colors. The next interpretation may be lines and all that. Next interpretation will be shapes and triangles and squares. And next interpretation could be, eyes and lips. And next interpretation could be faces. Next interpretation could be body, and next interpretation could be actions, right? So you see, there are many, many layers of interpretation needed sometimes, and simple machine learning systems are not able to do that. So that is why in the last 5-6 years, we have seen a birth of new kind of machine learning called deep learning, and that is becoming very common. And this is specifically designed for such problems where the raw data and what you want to interpret out of it is very big. And that is where deep learning comes in. And it mimics the human brain's process of, layers and layers of processing before it can interpret something. So that is deep learning. So we understand what is AI, what is machine learning, and what is deep learning. Now there's another terminology that we all use, which is what we call data science, right? Data science is a very broad set of technologies which combine things in AI, in machine learning and deep learning. And data science is really the engineering and the technology part of all of this. And really, the goal of data science is to take raw data from the business, to understand domain, to formulate the AI architecture, to see where we want to use deep learning, where we want to use machine learning, where we want to use artificial intelligence. In other words, where the data is very complex, like vision and speech, where the data is simple, like multivariate data, so we can build simple models, and where we need reasoning and thinking and optimization. So think of all of this have to come together in order to build the overall system. And that is what data science does. It's a combination of all of these to put together. So let's look at some of the broad ML AI paradigms that are available to us. And you can think of this, the analogy that I would draw is, let's say you were becoming a chef and you wanted to learn different aspects of being a chef. So you're going to learn, let's say the nutrition part of chef, food, the different arts of cooking and frying and baking and all that. And once you've learned those different things, then you are ready to prepare any dish. So preparing a dish is like building a AI system for a company. But before you do that, you have to know what all skills are available, what all paradigms are available, right? So similarly, in machine learning, there are many paradigms, and we're going to cover some top most important paradigms, and that will give you a good depth understanding of. And each of these paradigms are going to be talked about in a greater detail in the subsequent modules. All right. So, at a broad level, there are four broad machine learning paradigms. One is supervised learning, and supervised learning is really about mapping an input to an output. Right. So you're given, let's say, the pixels values from a satellite data, and you want to predict what is actually on the ground. So that's a classification example. Or you're given some parameters of something, and you have to predict a number. That's a regression example. The second paradigm is what we call the unsupervised learning paradigm, where we are going to find structure in data. So nobody is asking us to map the data from an input to an output, but we're trying to say, hey, here is a lot of data. What is the structure in it, right? What kind of clusters do you see? Where the data is more? What kind of patterns are repeating? And what kind of important structures to be found in the data. So that is all unsupervised learning. And babies do a lot of unsupervised learning in the early development of the brain, and then later when they develop languages, then they know that this thing that they are seeing is a door or a chair or a letter A. That is when supervised learning comes in. So we also transition from unsupervised to supervised in some sense. Another important paradigm is what we call semi-supervised learning, which is a combination of supervised learning and unsupervised learning. So the idea is you have lots of unlabeled data and you have very little labeled data. How do you take advantage of both? And that is what the semi-supervised learning paradigm is. And we'll talk about that. And last is what we call a reinforcement learning paradigm, which is very different than all these supervised and unsupervised. Here, really, you are learning a sequence of actions so that you can get a reward at the end of it. So, for example, when you play a game of chess, you want to know what to play in the next move and all that. So, these are all examples of reinforcement learning paradigm. So now let's talk about the supervised learning paradigms and see what are some of the key supervised learning paradigms available to us. So when we say supervised learning, what do we really mean is the following. So imagine that you have lots of training data where you are given a pair of, here are the inputs, here is the output you have to map it to, right? So for example, when a child is looking at a notebook and seeing a squiggly thing on the sheet, that is the input, what the eyes are seeing. But when the mother says or the teacher says this is letter A, that is the output. So the child is trying to learn a mapping between the squiggly shape on the paper and the letter A, which is a class label, right? So there is always an input-output mapping. Similarly, when we looked at Google Images that they want to do captcha on, they can they'll give you an image of an OCR image as an input, and the output is what is the name of the thing, like the word morning, or is it a traffic street light or what have you, right? So there's always a input output mapping. Similarly, in medical domain, input could be a set of symptoms, right? So I have a headache, cold, cough, this and that, and then the output could be a prediction on a disease, right? So input output thinking is what makes the supervised learning paradigm. So obviously the first thing we need is a lot of training data, lots of pairs of inputs and outputs. And then we have to actually start learning the relationship. So we have to say, whenever the squiggly shape is like this, it is A. Whenever the squiggly shape is like this, it is B. So how do you transition from the raw input to extracting the features that we talked about earlier, to then learning a mapping between those features to the output label? So that is the training phase that happens in the supervised learning. And once you have trained a model and you have deployed the model and say, now my model is trained, it can do things live, then we do inferencing and we say a new input has come. We send it directly to the model and the model says, oh, this is letter A, this is letter B. So you see that an intelligent system is constantly in the training mode as well as inferencing mode, right? So there is no such thing as training forever and then suddenly start inferencing, right? So all AI systems are a loop. They train a little, they make some mistakes in the inferencing, but over a period of time, the training kind of makes them more and more perfect. Yeah. And so just remember these three aspects of supervised learning. We're going to think of a mapping between input and output. We're going to need a lot of labeled examples. And we talked about the importance of labeled examples. And then we're going to have a training process and an inferencing process. Training process is helping us build the models. Inferencing process is helping us use the model to draw inferences in the real world scenarios. So within the supervised learning, there are two broad paradigms that we'll talk about. One is classification, one is the regression. And let's look at the difference between these two. So if I have a set of inputs, right? Let's say I have a student and I have all of his grades and all his habits and all the other parameters, and I want to just classify and predict whether such a student will pass or fail. So pass and fail are two, symbols, if you will, right? It's a binary classification, right? So there, this is an example of a classification problem where the input can be anything, but the output is a discrete variable, either this or that, right? So that's a class label. So that's a classification paradigm. But the same data about the same student can also be used to predict a number. How many marks will he get in physics or in chemistry or in math, right? So now we are predicting a number, and that is a regression problem. So whenever the output is a number, it's a regression problem. Whenever the output is a discrete variable, it's a classification problem, right? And that, this itself is a classification problem. What is a classification problem and what's a regression problem is itself a classification problem, right? So we understand this idea of classification versus regression. Both are necessary because sometimes we just have to assign labels, sometimes we have to figure out a number, right? So we'll see a lot of examples of this. So a typical classification scenario looks like that. You're given two classes or more. You have to have at least two classes. And you're given lots of data of one and the other type. So think of computer vision systems where they're given lots of data for object type 1, object type 2, object type 10,000. And now they have to learn how to distinguish between all the classes and say when a new image comes in, does it belong to this class or that class, right? So this is the dog versus cat classifiers. There's a notion of data points. There's a notion of labels on the data points, the blues and the greens. There's a notion of decision boundary that we are trying to learn. And then when we do the inferencing, a new image comes in, we can tell whether you are on one side of the decision boundary, so you are a dog, or on the other side, so you're a cat, right? So that kind of thing is a classification paradigm. Now, the same data can also be used to do regression. So now let's say we want to learn a mapping between height and weight, right? So as the height is increasing, the weight is also increasing. And this is something that, pediatricians do all the time with children. They measure their height and weight and they go to a curve and they say, is the growth normal or overweight or underweight, right? So we can tell all that because we have a regression model. So learning this relationship between an input and an output, where the output in this case is a weight, input is a height, is a regression problem because what we are learning is a mapping to a number. Let's take another example of classification paradigm. So imagine you are running a vehicle insurance company and you want to predict whether a particular policy holder is going to renew the policy or not, right? So the idea is you're building a classifier now because what you're trying to do is you're trying to predict a yes and a no answer and whether they will buy or not buy the policy. So again, you're going to look at a mapping mindset where you're going to think about what are the right features to look at, right? So is it a male or female? What is the age group? Does he have a driving license? What is the age of the vehicle? What are the previous premium amount? So imagine this is what is known before you make a prediction, and all of this is relevant, right? What may not be relevant is the color of the vehicle, for example, right? So those are what we call irrelevant features, and these are what we call relevant features. So we pick all the relevant features based on domain knowledge and call them the input vector, And then we pick the output vector and we create this labeled data. And then we can use any kind of a machine learning paradigm, classification paradigm, to actually learn that. So we can build a decision tree or a neural network or a support vector machine once we have this labeled data with us. So creating this labeled data is one of the tasks that a lot of companies do. Now note that the output here is a discrete value, 0 or 1. It's not a number 0 or a number 1. I could have called it yes, no also, or true, false also. So it's not a number 0 and 1 that we are predicting. We are predicting probability of 1 and probability of 0, or probability of buying and probability of not buying, right? So that's how a classification problem is set up. So there are a lot of classification problem examples out there, right? So if you look at Google builds hundreds of classifiers on the web pages, right? Is it a spam versus not spam page? Why does it need it? Because if a web page is showing up as a result of a query, first it also goes through a spam filter, because there are a lot of spam web pages out there. So they don't want to show them, right? Similarly, YouTube again builds a lot of classifiers, right? Like it's a adult content or a normal content. Is it a cartoon content or a regular video, right? So all kinds of classifiers are built on videos. LinkedIn again, builds a lot of classifiers, right? What kind of a skill set a person has, what kind of a role or a job type, is it a software engineer profile or is it a HR profile? Again, it builds a lot of classifiers. Right, Flipkart, for example, Amazon, Flipkart, telecom companies, they build a very important classifier called a churn prediction classifier that says, given the past history of the customer, what is the likely that this customer will churn in the next 3 months or will stay with the business? It's a very important classifier to build, because that will help you, understand customers and their, experiences, and you can intervene and say, hey, can I do something so that this customer does not churn? Another very classical example of classifiers is our emails and inbox, right? So Google has been improving the inbox for the last 20 years, and now our emails automatically go to the right folders, right? We don't have to do it. Why? Because Google has already built a classifier that says if there are certain keywords like travel and book a flight and all that, it will go into one folder. And if there are other keywords like it's important, it's urgent, or whatever, it goes to a primary folder, right? So again, based on whatever data type we have, whether we have a video, whether we have an image, the input doesn't matter. What matters is the output. And as long as the output is a discrete value coming from a set of possible discrete values, it becomes a classification paradigm. Yeah. Gene sequences again, can be classified. Will you have cancer or not, Parkinson's or not, diabetes or not, COVID or not, or whatever, right? So these kind of things can be done. Similarly, remote sensing, we are giving a lot of sensor data per pixel, and we can classify them into one of the land cover types, right? So that's a classification example. So now let's take an example of a regression problem. Again, the setting is the same. We have insurance company. We have the same customer data, but now we are going to predict something different, right? So here we have the same input data, gender, age, driving license, vehicle, and all that. But now we are predicting an output which is not a class label, but it's a number. So let's say we are trying to predict what should be the new proposed premium which a customer is going to take or not take, right? So we want to now predict a number instead of a class label. So this is an example of regression problem. So the same business can use the same data to either build a classification or a regression problem, right? So it's not a choice of this versus that. Generally, businesses need both and more, right? So just to give you a sense of the key differences between regression and classification. So again, there are lots of areas where regression is applied. So I'll give you some broad examples. So one is obviously stock market prediction, and the very, very large businesses like the stock companies and in the New York and Bombay Stock Exchange are working on how do you predict the stock tomorrow, right? Whether a stock will go up or down is a classification problem. How much up and how much down it will go is a regression problem, right? So will it increase by 10% or decrease by 3% is again a regression problem. We are predicting a number. Similarly, demand forecasting is a very big area in all domains, right? If you look at telecom, we want to do demand forecasting of how much data will be consumed at this time of day on a weekday in this part of the city, right? Similarly, in retail, we can say, which products are going to be needed more, where, right? And by what kind of customer. So this is all demand forecasting. Demand forecasting is posed as a regression problem because demand is a volume. And now, if I'm selling 10,000 products, I have to do demand forecasting for each of the 10,000 products in each of the context, location, and time. So it's a very complex, very large scale problems that businesses have to solve in order to optimize their supply chain, right? So you cannot optimize your supply chain unless you know what is going to be the demand. And this is going to be needed more and more. For example, in agriculture, we have a demand supply situation, and in companies like Ola and Uber, there is a demand supply situation. In companies like Swiggy, where they do food delivery, there is also demand supply, right? So in all these examples, demand forecasting becomes a very important paradigm. Another paradigm that is very important is price prediction, especially pricing optimization, right? So what we do is we build something called a conversion model that says if this product is sold at this price, what is the probability that a customer will buy it, right? And that is called a conversion model, which is again a regression problem paradigm combined with the classification paradigm. So you have to optimize the price because it's a number, and but you have to predict the conversion probability, which is a classification, right? So how do you predict pricing? And the right pricing is a constant problem. If you think about all the retailers doing pricing optimization all the time, and that is based on the season, their inventory levels, and their prediction of demand, and the competitor pricing. All of this goes as input, and the output is the optimal price for something. Yeah. A lot of times, Ola, Uber do pricing at a very, very fine grain, right? Every 5 minutes, they redo the pricing for a location because during peak time, the supply demand is changing all the time and the pricing is updated all the time, right? So pricing can be a very, very fine grained decisions also. Another kind of thing that companies like Google do is they do what we call click through rate prediction. And they say, what is the probability that somebody will click on this result at this location? Now, that looks like a classification problem. Will they click or not? But ultimately, what they're trying to predict is a click through rate. It's a number. Is a click through rate going to be 5%, 10%, 50%? And that number is being predicted all the time, right? So that's another example of a regression problem. Another is, percentage watch prediction. For example, if YouTube is trying to say, is this a good video to show to this person at this time? They are going to predict what fraction of the video somebody will watch. So again, it's a number you are predicting between 0 and 100. So that's a regression problem, right? So in the weather world, for example, weather forecasting is full of regression models. So they're trying to predict humidity, temperature, pressure, all of that. So those are all regression problems. If they're predicting whether it is going to rain or not, that becomes a classification problem, right? But how much will it rain is a regression problem. So you see, the same business using the same data can mix and match and say, is this a regression or a classification problem? And this is something you have to think about in every domain. I gave you enough examples to understand how these two paradigms work. Yeah. Okay, so the next thing is we'll talk about the unsupervised learning now. So we understand supervised learning has classification, regression are two major paradigms. In unsupervised learning, the goal is that you're not given an output, you're only given a raw input data and you're asked to find something interesting in it. It's like needle in a haystack. You have to find something interesting in your data. So for example, you can say, how many segments are there in my market segment, right? Or where the population is high, right? So those kind of models. So we'll see some of these unsupervised learning paradigms. So here the idea is you are only given the raw data, right? The gray area, which is all the raw data. So imagine if I give you all the web pages on the internet, or all the YouTube videos on YouTube, or all the LinkedIn profiles, and say, what can you do with it? So what I don't know is how many segments are there in my data, how many types of web pages are there on the internet, right? How many types of profiles are out there? What kind of emails do I get, right? And that is the level of ignorance that unsupervised learning is able to handle. And all we have to tell is, hey, can you cluster the web pages into 200 types of web pages, or 30 types of YouTube videos, or 50 types of pixels on the ground? And can I use clustering, for example, as an unsupervised learning paradigm to find structure in the data, right? Not to classify it into one type or the other, right? So my favorite way to understand the difference is, imagine that you are reading a book and you are told that this is the question paper that will come, right? So if you look at the question paper first and then you read the book, then it becomes a supervised learning paradigm where you know what you are supposed to know from the book, and you read the book differently now, right? Because you are reading it based on the question paper that you are being asked, right? So that is called a supervised learning. Unsupervised learning is when I say, hey, here is a book, read everything and tell me something interesting. There is no specific question I'm asking, but I want you to summarize it or tell me what is the patterns in it or what have you. That becomes an unsupervised learning problem because there is no goal. You just got lots of data and you have to figure out what is interesting in it. So in human learning, when children are learning to walk or um, speak and all that, they're not going to a grammar school, they're not going to a language school, they're not going to a school at all, and they're just picking up lots of patterns in the way they hear the words and the sounds. So they pick up the words, they pick up the grammar of a sentence in the mother tongue without actually being formally trained or supervised learning happening, right? So unsupervised learning is actually a much more powerful paradigm than supervised learning if you think about it, right? And that's a very important area when companies need it. So let me give you another anecdotal example of this. When does a company transition from an unsupervised to a supervised paradigm? So imagine that you have opened a new business, let's say Ola Uber type of business, and you've started running your business and lots of people are using it, and you decide that you need feedback, right? So then what do? You don't know what categories of feedback you need in the beginning. So what do? You just put a text box and you let people type whatever they want to type, right? It's kind of like what feedback people do in for example on Twitter or social networking. So you get a lot of feedback which is of text type, and you don't know how many types of feedback you are getting. So at that stage, we apply what we call an unsupervised learning problem. We say, let's assume that there are 5 types of feedback we are getting. So let's do a clustering of this feedback text data into 5 clusters. And then when you start looking at the clusters, you start to see that, oh, there are password problems, there are driver problems, there are car problems, there are traffic problems, there are share right problems. Then you start to create structure and understand structure in the data. Then you start to discover the different categories in your data. Earlier, you did not know. And once you discover that there are 20 things that people are complaining about, or 5 things people are complaining about, then you go to a supervised learning paradigm. So, what you've done, you've used unsupervised learning to actually discover class labels. And now, after 6 months and doing all this, you change your app, you change your feedback system, and you say, now I'm not going to give you a blank text box. I'm actually going to give you 6 options. You pick one of the 6 options, or you have a blank text box. So now the same company has moved from an unsupervised learning paradigm to a supervised learning paradigm using this learning from the raw data itself. This is a very important transition that children do when they go from unsupervised to supervised. Similarly, companies do when they go from unsupervised to supervised. Yeah. And same thing Google did when it started, it was downloading the whole internet. It didn't know what type of classifiers it should build. So it said, let's do clustering first. And then it found out that there are pages of this type and that type. There are news pages, there are sports pages, there are blogs, there are scientific pages, there are home pages of people of all kinds. And then that structure emerged. And from that structure, Google then built a bunch of classifiers later, right? And then it becomes a supervised learning problem. So imagine that you are given a lot of data around the segment of your customer, right? So you have a census data that says gender, age, income, and score. And now your boss says, "Hey, I want to run a campaign, and I have 5 types of campaigns I can run, but I don't know which campaign is useful for which person." So what do? We say, "Okay, I'm going to do unsupervised learning and figure out similar groups of people, market segmentation. I'll create 5 market segments, and then we're going to look at them and then decide which campaign is best for whom." So that is how discovering structure in the data and is important. So here we are given a bunch of input variables. What we are not given is any output variable, right? So we are not saying map this input to a certain output. What we are saying is, here is a bunch of input variables. Can you find structure in it? So that's an example, and we're going to study a lot of unsupervised learning paradigms, including clustering and pattern recognition. So one of the most common unsupervised learning paradigm is called clustering. Clustering is really about grouping similar things together, and we do clustering all the time. We have clustered the plants and animals into different, org structure. We have clustered colors into, for example, warm colors and cold colors. And we have clustered products into electronics and grocery products. So clustering is a very common paradigm, and we use this in data science. So in this example, what we have done, we have taken last 10 years of retail data for a very large electronic retailer. And instead of looking at customer from their demographic point of view, we have tried to group them by the what they buy. So if you represent the customer by the set of products they have bought in the last, let's say, 6 months, and we find similar customers together, and we divide the customer base into 50 segments. So some of the segments are about movies that they buy. Some are about Xbox products that they buy. Some are GameCube. Some are PlayStation kind of customers. Some buy a lot of movie, computer related, hardware related things like memory, CPU, and all that. And a lot of clusters are coming that are buying appliances like dishwasher and all that, right? So now, how do you use this information to actually make a business transformation? So how do we go from broadcast decisions to personalized decisions? And broadcast decision is to send, let's say, one set of coupons to all the customers, and obviously the cost of doing that is low, but the ROI is also very low, the conversion rate is very low. But if we do this very simple clustering, we can now send the right coupons to the right customers, and we can create different campaigns for each customer segment. And now the customers are going to receive the coupons that are very relevant to them based on the products they have bought in the past. And what this does, it does multiple things. It reduces the cost of marketing, it improves the conversion rate, and the most important is it also improves what we call customer fatigue or coupon fatigue of a customer. Because if we keep sending them non-relevant coupons after non-relevant coupons, eventually they start ignoring your coupons, right? So that is the bigger problem of a broadcast decision. So this is a very simple example of how behavior-based clustering can actually transform a very important sales and marketing decision, which can lead to a much better customer experience. All right. So the next paradigm that we'll talk about is an outlier detection paradigm. This is again a very common paradigm today. It is used whenever we are detecting fraud or something out of the ordinary, right? So imagine that somebody is swiping a credit card, and we have built a model for every credit card user in terms of how much they spend, where they spend, when do they spend, what kind of stores do they spend, and all that. So every customer has a regular normal behavior. And now, let's say somebody steals your credit card and starts using it in a very different place, in a different way, for a very different amount, and something is wrong. Something is an outlier in that behavior. And these credit card companies can figure that out with one or two transactions. They will know that something is wrong here. This is not a normal behavior of this customer. And they will either block the card or make a phone call and say, "Did you make this transaction or not?" Right? And all of us would have gotten a call from the bank about a particular transaction. It is because of these kind of things, right? So that's an example of an outlier detection. Similarly, today we are struggling with cybersecurity all the time, and if you look at how a normal application, uses the services of a microservices environment, it'll do a certain sequence of calls, right? Like when you log into a bank, you make one or two attempts to log in, then you check your account, then you do an FT, you break an FT, you do this, you transfer the money, and then you get out. So that's a normal behavior in a banking scenario. But if a hacker is actually doing this, they will not do it in a normal behavior, right? So they'll try to log in maybe 4 times instead of once. They will try to, go to a web page but not complete the transaction. They will go to random transactions and all that. They're trying to find holes in the system. So their behavior is very abnormal compared to a regular user's behavior on the banking website. So this kind of thinking where you can learn the greens, which are all the normal behaviors, and then you are detecting the reds, which are all the abnormal behaviors, is a very interesting paradigm in machine learning and in unsupervised learning. Yeah. This behavior is used in, like we said, fraud and hacking. This is also used in anti-terrorism activities, finding criminals, anywhere there is an abnormal activity. Similarly, this is used in your Fitbits where they say, look, your heart rate is normal, but suddenly on a certain day it became abnormal, right? ECG and all that, right? So that's also we use a lot of outlier detection. So the same paradigm used in multiple places. Another very important paradigm is pattern recognition, which is about what things go together or what things go one after the other, right? So, for example, here um, we have taken a lot of data from IMDb movies, and we have keywords that go with other keywords, right? And now we can say that what keywords go together and what group of keywords make a logical sense. So here we are talking about one group of keywords that were discovered, another group, another group. So these are patterns that emerge from data. And we didn't know how many groups are there. We didn't know how to group the groups together. And this system doesn't understand English. For it, this is all an ID. And it is able to figure out that these two, items are going together in lots of movies, these two keywords. So there must be a strong connection between them, and then using that graph it can now figure out patterns on the graph, which are these connected components, right? So this is an example of pattern recognition. Another very common pattern is the language patterns, right? So whenever we speak a language, and if I change the word of the order, see, if I change the word of the order, suddenly your brain is saying, oh, something is wrong, right? It should be I change the order of the word, right? So that is also a pattern, and our brain kind of understands patterns in sequential or sets or structures of other types. And these are pattern recognition problems that machines can do, right? They can look at lots and lots of data and find out the right patterns in the data. So the next machine learning paradigm we'll talk about is what we call semi-supervised learning, right? So this is, as the name suggests, it's a combination of supervised learning and unsupervised learning in some sense, right? So, you have lots of unlabeled data and a very small amount of labeled data. So when you are doing supervised learning, you're only using the labeled data part of it, right? So example is, let's say you have all the YouTube videos on YouTube, 10 billion of them. So you have lots of unlabeled data. But let's say you have only labeled 10,000 videos as cartoon and 10,000 as non-cartoon. So you only have 20,000 labeled examples, right? So if you only use the 20,000 labeled examples to build your classifier, that is supervised learning. If you take all the 10 billion YouTube videos and do clustering on them, that is unsupervised learning. Now imagine the third scenario where we take the label data of the 20,000 videos, we build a model of cartoon versus not cartoon, we apply this model on all the 10 billion videos, and the model does a classification of all the 10 billion videos, and out of that we take the ones which are very highly confident and say these are definitely cartoons and these are definitely non-cartoons. Now let's take 100,000 videos of both types and now call them cartoons and non-cartoons, add them to the 10,000 videos of the two classes. Now we have 100,000 plus 10,000 as positive and negative examples. So what we have done, we have utilized the power of unlabeled data by the first model that we built. We created more labeled data, and now we can build a second version of the cartoon versus not cartoon classifier. So this paradigm is what we call a semi-supervised learning paradigm. Yeah. So let's take some more examples of it, right? And so look at satellite data. Again, we have lots and lots of satellite data. Every pixel on the earth, we have a satellite view on it. But we have done very little labeled data out of it. So what do? We use this to build the first version of the model, only using the very small number of labeled and unlabeled data, and say this belongs to this class, this belongs to this class. Once you have built that model, we can apply that model to the rest of the gray area. And now, uh, we will label everything and say this is green, this is red. But wherever we have high confidence of green, we will take that. And wherever we have a high confidence in red, we will take that. And now my label data has grown from the dark regions to the light regions also. So now we have a lot more label data than before. And I didn't have to spend the time to actually go to those pixels on the ground and collect the label data. We were able to use the previous model itself to generate a lot more label data on the unlabeled examples that I have, right? And then we can now build a new model using the pink area and the light green area, because now we have lots and lots of label data compared to before. So this process is what we are calling semi-supervised learning. So let me show you this as a process. You start with a few labeled examples. You build and optimize your initial classifier. That classifier is not a very good classifier because it has very few labeled examples compared to the overall number of data. Then you have lots of unlabeled data that is coming from the bottom, and then you classify them using your first model, and then you pick the ones that have a high degree of confidence, right? So if a classification output is a 1, a probability of 1 or a probability of 0, you don't pick anything which is in the middle. So you say any example that a classifier has classified above zero point 0.9 will go to the blue class, and below zero point 0.1 will go to the orange class. So now these are high confidence classes, and we have labeled lots of data with those high confidence, and now they became part of our new training data, and then we can retain another classifier, right? So this process is what we can call a semi-supervised learning paradigm. Yeah? Again, there are lots of examples of where it is applied. And the typical situation where it is applied is where the unlabeled data is a lot more than labeled data, like remote sensing, web scale text mining. Internet is full of text data, but we have very little labeled data on it. Radiology images, we have lots of images that are in the hospitals all over the place, but and they need a lot of labeling. But in the past, we have labeled data. We apply the model, we get more labeled data, and we can do better radiology. Google Street is an example where you have cars running around, lots of data is being collected. All that is unlabeled data, and unless somebody labels it using CAPTCHA and other such things, it doesn't become labeled data, right? And again, Google Street can use this kind of an approach to label its data very, very actively. So another paradigm that we'll talk about is the reinforcement learning paradigm. It's a very different paradigm than supervised, semi-supervised, and unsupervised paradigm. And it's now becoming more and more popular, and we'll see why. Yeah. So what is a reinforcement learning paradigm is that imagine how a child learns to walk, right? So let's take a very classic example of reinforcement learning. And really, the real instruction that the brain needs to give is to every muscle how to operate, right? When to stretch, when to become stiff, when to loosen up. So imagine the brain is trying to learn how to control the muscles so that the child can get up, the child can balance, and the child can run and walk, right? Now, what happens is when the child is learning to walk, uh, we are not giving supervised label that says, now you stretch this muscle or now you loosen up this muscle. We are not telling that. So this is not a supervised learning problem. But how does a child do? So the brain gives random instructions in the beginning to the muscles. The child is either able to walk or not able to walk. And then the brain learns that what I did was right or what I did was wrong. automatically, right? So it's not about telling the muscle exactly what to do, but it is about giving a feedback or a reinforcement at the end. So when the baby is able to walk and it gets a positive feedback, or if it falls and it hurts itself, it gets a negative feedback. So it's the feedback data that becomes the label, and not the specific instruction on what to do in each state. When you are balanced this way, what do you do? So we're not telling the exact answer at every stage, but we are giving a final compliment or a final, reward or punishment, and that is what leads to the learning of the rest of it. Right. So this paradigm is very different. It's neither a classification or a regression paradigm. It's a reinforcement learning paradigm. And we do this all the time when children are learning. They do a good thing, then they get positive reinforcement or a negative reinforcement. Right. They're not told what to do, but when they do something, they get a positive and negative reinforcement. So that behavior is exaggerated. Yeah. So we look at a lot of examples of these. So one classic case of this is pole balancing, and all of us have done pole balancing in the past, where imagine you have a pole you're trying to balance, and now you can move the hand left or right. You can try to balance the pole. The pole will eventually fall, or it will stay, and it can stay longer, it can stay shorter. And in this video we are showing how different trials were done, and the system is collecting the data all the time, and it is learning, and after 100 iterations and 179 iterations, the system is now able to learn how to do pole balancing by itself, right? And all that. So this is an example of a reinforcement learning paradigm, where we are not telling the pole or the base to move left or right. We are not telling that. We are just saying, in this state, if you did this, eventually you fall or eventually you stay. And that eventually you fall, eventually you stay is what the reinforcement signal is. Right? So that is the paradigm that is a pole balancing paradigm. So now let's talk about the nuts and bolts of how a reinforcement learning system works, right? And there are three important ideas in reinforcement learning. So we'll talk about that. So here's the first question. Imagine you're doing pole balancing, and now you want to define the state of the pole. The idea that what is the pole, the state of the pole could be defined in terms of a set of numbers, right? So what are those numbers? So I'll let you think about it. Um, All right. So now the three things that you will think about is, for example, what is the position of the pole? Is it vertical? Is it slightly to the left or to the right? Which direction it is? What is the angular velocity of the pole? Is it falling? Is it not falling? And what is the angular acceleration of the pole? Is it falling with a higher acceleration or a lower acceleration, right? So because gravity is involved. So this is how our brain kind of figures out the state of the pole. So the state thinking is very important. Then comes the action. So given that you are in this state, should you move your hand left or right? Right? That is your action. The direction in which you want to move your hand, the velocity with which you want to move your hand, the acceleration with which you want to move your hand, that becomes your state vector, right? So there is action vector. So there is a state vector, which is what do you observe, and the action vector is what do you do if this is what you observe. Yeah. And the third thing is the notion of reward or success. So what is the notion of reward or success in pole balancing? That eventually, were you able to hold the pole for a long time, or did it fall, right? And obviously in the last thing you did, it fell. So you know that this is the last thing you did, but every time the pole comes back to normal, you get a positive reinforcement. Every time it falls, you get a negative reinforcement, right? So we understand the idea of the feedback. Now the feedback you are getting is not on every little action that you do, but at the end of all actions. So this is what happens in reinforcement learning. You don't get to know your final reward until you have played the full game, right? And reinforcement learning is used by AlphaGo and chess, learning systems to play lots of games and decide what is the state of the game and what is the action to be taken, and then what is the reward function. So just remember these three constructs in a reinforcement learning scenario. So in general, reinforcement learning is learning by exploration and reward. There's no direct answer. You're not given a class label. You're not given a number to predict. You're given a reward function. And now your goal is to learn that in many situations, how do I map my input, which is the state vector, to an output, which is an action vector. And the goal is to maximize the eventual reward I will eventually get, right? So one way to look at it is, imagine you have an agent which is the learning system, whether it's a child learning to walk or a person learning to play a game or a AI system learning to play a game. These are all agents, and basically they observe the current state as t, and based on that they take the current action at, and then the environment gives them the feedback and say this is the reward you are going to get and this is the next state you are going to move to, right? Like in a game of chess, if I am the agent trying to learn, I'm trying to play a move which will maximize my probability of winning the game eventually. And now make a move, and the environment is the other player. So anything that you can only observe but not control is the environment. So the environment tells me that this is your reward function. Whether you won the game, lost the game, you lost a important piece in the game, all that you will learn. And then the game has moved on to the next state. So this cycle is what happens, and this cycle is what we go through in a reinforcement learning scenario. So there are many applications of reinforcement learning that out there, and one of them is, for example, the gaming industry, right? So if you recall, Google bought this company called DeepMinds, worth almost like $500 million. And that company had mastered the art of reinforcement learning, and especially in the gaming world. And one of their claim to claim is the AlphaGo program, which is able to now beat the best human at a game called Go. And Go is a very complex game compared to chess. And people never thought that machines will be able to learn the level of complexity that Go has. But with this company, they are able to figure this out. And the way these companies learn these games is very simple. What they do is they say that this is my current learning of the game. Then they simulate a game. They say, let me invoke one player and another player, and let me start with the first state of the game, which is the initial board position. And then the first player plays a move based on the current learning of the game. Then the second player uses it to learn, play the second move. And they play the entire game. They record the entire game. And then they see what was the outcome. Now imagine doing this on a cloud and doing millions and millions of games you can play. You can collect lots of data. And all that data can now be used to learn your paths and say, this is the right path or this is the right action in this kind of a thing. So here we are not teaching the strategies of the game explicitly. We are letting the system automatically learn the strategies. The only thing we are doing explicitly is the rules of the game have been told so that the system doesn't make a wrong move, but from a rules perspective, but strategies are not told. And that is now possible in reinforcement learning. So you can imagine how powerful reinforcement learning paradigm is, right? Now people are using it in many other places, including driving a car. So again, driving a car smoothly is a sequence of actions, right? When do you speed up? When do you slow down? How far from the red light should you slow down? What are your reward functions in that case, right? All of that. So deep reinforcement learning is now used a lot in these sequential tasks, right? Like autonomous vehicles. In agriculture, right? If you want to think about agriculture as a sequence of decisions, right? What to grow, when to water every day, when to fertilize, when to do other things. Again, it's a sequence of actions we are learning. And the reward function is the yield at the end of the day. And say, did I get the right yield? Did I get more yield or less yield? Or did I destroy the crop? Or what was the soil condition after the crop? All of this can be added to the reward function. And now we can learn how to do farming better and better through an AI system, if we can collect all that data. Similarly, if you think about robotics, again, completing one task in robotics, right? Whether it is Amazon robots trying to pick a packet from somewhere and then putting it somewhere, it's a task, it's a sequence of actions, right? go left, right, go up, down, turn this way, that way. And they're, instead of programming that into the system, can you actually make it learn like humans do? And think of our own muscular system as a robotic system. And we learn many things. We learn to walk, we learn to swim, we learn to do yoga, we learn to you do horse riding or motorcycle riding. All these are reinforcement learning tasks. And all these we have learned because of our ability to do the task multiple times and figure it out, how to use our muscles better to do all these tasks. So let's understand deep learning in a very simple way. And it's not something that we have to know in great detail, but we just have to know what is the place of deep learning in the overall system, when to apply it, and on what kind of data and what kind of problems we apply, right? And how is it different than machine learning? So, in the overall scheme of things, we have AI as a broad umbrella. Within that, we have machine learning. Within that, there is a type of machine learning architecture called neural networks. And there is a type of neural network which we call deep learning. So, deep learning is nothing but a very, very specific kind of a machine learning system, right? Now, how is it different and unique is what we have to understand, and when to apply and how to appreciate the birth of deep learning and why is it needed is very important, right? So one of the key distinguishing features is the following, right? So imagine that in a traditional machine learning path, you get to see let's say an image of a car. If that is an input, then there is a human who is involved in actually coming up with features. And he's saying, if you can detect something like a light, if you can detect, a door, if you can detect this or that, right? And then I will add these features manually into the system, and then I will be able to build one classifier which is car versus not car, right? And that's an excruciatingly painful process, because the number of features you have to extract for just a car versus not car is too many, and these features can be at any level of complexity. And you have to do thousands of such objects, right? So manual work of feature engineering is not practical in such complex domains like images and videos and all that, right? So what does the deep learning system do? It takes the image of a car and it does a feature engineering automatically, right? And it says the first few layers, like I said, right, detect vertical lines, horizontal lines, simple shapes, then complex shapes, and all that. The first few layers, or first 10, 15, 30, 50 layers in a deep learning is just about increasing the semantic notion of a feature that you're extracting, and you're not doing it for a particular object, you're doing it universally across all objects you want to detect. And it says that, look, in the third layer, detecting a vertical line, horizontal line is a good feature. Why? Because in the 100th layer, it is going to help me distinguish between a car and a truck, right? So this depth is what comes automatically, and you don't have to actually program this depth. All we have to do is design a neural network architecture which is deep enough to capture this much of complexity, and you have to provide lots of label data, and then the system works. And the early layers in the brain, the feature engineering layers are built when the babies are going through just the surroundings and looking at the world around them. They're building features like edge detection is important, right? The brain is already learning that. So the lower layers are built first, and then on top of it the later layers are built, the supervised layers, right? So you again see unsupervised supervised transition happening in the early layers of deep learning to later layers of deep learning. So here are some more, examples of where it is being used. So right now, people are using it in speech recognition, Alexa, Siri, Google Voice. Lots of label data is used to create very accurate speech models, speech to text models, and all that. Image recognition is being improved all the time by these kind of systems. Google Lens, for example, is a great example where they have combined OCR and object recognition and location intelligence together and say, this is where you're standing, this is where you're pointing, and by the way, this is what the dashboard is saying on the walls. and this is what you are seeing. So now imagine you can do systems like, hey Google Lens, can you help me cross the street? I'm a blind person, and then it can take you across the street, right? That kind of thing. So it can be your visual companion because it has almost a human-like ability to see now. Yeah. Chatbots is another example where we are learning deep, chats. For example, instead of programming a chatbot to say, if you say this, I will say that, can I learn a chatbot by just giving lots of examples? So earlier we talked about a doctor-patient conversation. Now imagine if I have recorded conversations from the past of lots of doctor-patient conversations. After preserving the privacy, we can give all that data to a machine learning system, deep learning system, and it can learn a hierarchical structure of what to say as a word, what to say as an utterance, and what to say as a dialogue, and what to say as a dialogue sequence of dialogues, right? So this is the hierarchical structure in a conversation, and deep learning structures systems are very good at learning such structures.